Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. This is my last class of this course. In this class, I will give some programming assignments. So mainly I will discuss 20 programming assignments, the 20 programming problems. These programming assignments you can do either in MATLAB or maybe OpenCV Python or maybe any other programming languages. So one by one all these programming assignments I will discuss now. So let us start now. So first programming assignment is consider an image containing one arbitrary object and after this apply affine transformation to show all the following cases. So first we have to show the rotation, after this translation, shearing, scaling and also the combined translation, rotation and scaling. So this concept already I have explained in my class, the concept of the affine transformation. So your output will be something like this. You can see I have the original image. This image can be rotated by 60 degree and also this image can be translated. So this is the translated image. This image can be sheared, that is the shearing can be done. That means the scaling is not uniform throughout the image, that is called shearing. Also we can do the scaling, scale image you can see, and also we can do the combined translation, rotation and scaling. So this is the concept of the affine transformation. So for this you have to write a program. The program in MATLAB or maybe you can use Python. The OpenCV Python also you can use. So in this case I am showing one MATLAB program. So here you can see first I am reading the image. The image is the Lena image and after this what I am doing, the resizing the image, so that resizing to make the computation first. After this I am showing the original image. After this I am considering the rotation of the image. So 60 degree I am considering. So first I am doing the rotation and this is the transformation matrix for the rotation. So you know the transformation matrix for the rotation is cos theta, sin theta, minus sin theta, cos theta. And also we have to see the minimum and the maximum coordinates for avoiding negative coordinates. So that we have checked in this part. After this I am doing the rotation. So I am finding the rotated image based on the transformation matrix. So this rotated image can be displayed. After this I am considering the translation. So for the translation I am considering the translation vector. The translation vector t is equal to 1 0 0 1 and based on this I am translating the image, the input image. So I can do the translation and I can show the result of the translation. So this is the IMSHOW result 2. After this I am considering the shearing. Shearing means the scaling is not uniform throughout the object. So for shearing I am considering this. So scaling along the x direction, scaling along the y direction I am considering, and from this I am considering the shearing matrix. After this I am doing this one, these computations, and finally you can see I am showing the result of shearing, IMSHOW result 3, that is the result of shearing operation. And after this what I am considering, the scaling of the image. So scaling along the x direction, scaling along the y direction I am considering, and after this I am doing the scaling, and after scaling I can show the result of the scaling operation. So you can see result 4, that is nothing but the result of the scaling operation. After this what I am considering the affine transformation, considering translation, rotation and the scaling. So for this I am defining the parameters, all the parameters I am defining, like scaling, translation parameter and also the rotation parameters I am defining, and based on this I am doing the combined operation. And after this finally you can see I am showing the result. The result is result 7, that is the result corresponding to combined translation, rotation and scaling. So this is about the first assignment. So in the first assignment the problem is I have to do the affine transformation of the image. The second problem is write a MATLAB program to show perspective, weak perspective and orthographic projections of an object in an image, and for this make suitable assumptions if required. So I am showing the original 3D cube and you can see the output corresponding to perspective projection. So first one is the perspective projection, next one is the orthographic projection, and the last one is the weak perspective projection. So in case of the perspective projection, so already I have explained, that is the distant objects appear smaller. In case of the orthographic projection, it is nothing but XYZ is projected onto XY coordinate. That is the orthographic projection. And in case of the weak perspective projection, it is nothing but the scaling of the X coordinate, scaling of the Y coordinate like this, and the scaling of the Z coordinate. So that is the weak perspective projection. So based on some assumptions, you can show the perspective projection, orthographic projection, and weak perspective projection. There is a mistake here in the spelling. It should be perspective. It should be perspective. So this is the second assignment. So you can do in the MATLAB. Third problem is, write a MATLAB program to determine the depth map by using the concept of photometric stereo. So this problem is already I have explained, that is the concept of the shape from shading. The shape from shading problem can be solved by the concept of the photometric stereo. So for this I am considering different light sources, and shading information is used to determine the depth information. So different illumination conditions or different lighting conditions I am considering, and you can see I am getting the image of sphere 1, sphere 2 like this, because I am considering different lighting conditions. That means I am getting the shading conditions. So from all these images I have to get the depth information. That is the concept of the photometric stereo. So images of a sphere at different illuminations. So different illuminations I am considering, and based on this I am getting the shading. So from the shading information I have to get the depth information. So here first, based on the principle of the photometric stereo, you can determine the albedo surface map. The albedo also you can determine, and from the albedo you can determine the depth map of the object. So principle of the photometric stereo already I have explained in my classes. So this is the output of this assignment, that is you can determine the albedo of the surface map. Albedo you can determine, and also from this you can determine the depth map. This is about the third assignment. The next assignment is, for an arbitrary object in an image, determine scene code and shape number. So here I am showing the original image, and this image or this boundary of the object I have to represent by using the scene code. So for this you can see I am showing the boundary of the object, that is the boundary of the input image, that can be represented by the scene code. The concept of the scene code already I have explained, and after this I can reconstruct the boundary from the scene code. So in the fourth result, that is the fourth image, that is the reconstruction of the boundary from the scene code. So this problem you can try, that is first from the boundary information you can determine the scene code, and again from the scene code you can reconstruct the original boundary. Question number 5 is, for an arbitrary object in an image, obtain Fourier descriptors to represent its boundary. So that means the Fourier descriptor we have to use to represent a particular boundary. So you can see this is the original image, and you can see the boundary of the original image that can be reconstructed by the Fourier descriptors. So corresponding to this original image, the boundary can be represented by the Fourier descriptors. After this boundary can be reconstructed by considering inverse Fourier transform, that is by considering the Fourier coefficients I can reconstruct the original boundary, that is the reconstructed boundary. Similarly, I am considering the rotated image, and corresponding to this I am reconstructing the boundary with the help of the Fourier descriptors. So for the rotated image also we can determine the Fourier descriptors. After this, by using these Fourier descriptors we can reconstruct the boundary. So all the properties of the Fourier descriptors can be verified, because there are many properties of the Fourier descriptors like scaling, rotation, translation. So all the properties I have discussed in my class. So all these properties you can verify with the help of these images. So you take one image and you try to verify all the properties of the Fourier descriptors. So this is question number 5. After this, the next question is write a MATLAB code to represent a boundary of an object by B-spline of order 4. Show the represented boundary. So here I am considering the input image, and you know, in case of the B-spline I have to consider some control points, and also the important point is order of the B-spline. So here I am considering the order is 4. So with this B-spline curves I can represent the boundary with the help of the control points. So in the figure you can see here I am showing the control points, and after this between these control points I am considering the B-spline curve of order 4, and like this you can represent the boundary of the input image. So this problem also you can see, that is the representation of the object boundary by B-spline curve. So that is one important problem, the B-spline curve. The problem number 7 is represent a texture by gray level co-occurrence matrix. So that is GLCM, and determine all the relevant parameters. So in my class I have discussed about how to determine the GLCM, that is the gray level co-occurrence matrix. So for a particular displacement vector you can determine the gray level co-occurrence matrix, that is the array, the Pij you can determine, and that is displayed as an image. So for a particular displacement D I can determine the co-occurrence matrix, the Pij, that array I can determine, and that is displayed as an image, that is the gray level co-occurrence matrix. And from this I can determine the parameters. The parameters may be the maximum probability I can determine, moments I can determine, the contrast I can determine, entropy I can determine, uniformity I can determine, homogeneity I can determine. So all these parameters I can determine, and this GLCM is computed from several values of D. So the GLCM can be computed from several values of D, and the one which maximizes a statistical measure computed from Pij is ultimately used. So that means I am repeating this, the GLCM is computed from several values of D, that is the displacement vector, and the one which maximizes a statistical measure computed from Pij, that is the GLCM, is finally employed or finally used. So that is the concept of the GLCM. So we can determine all the relevant parameters. The parameters like the maximum probability, moments, entropy, all these parameters I can determine from the GLCM. So corresponding to this original image I can determine the GLCM matrix. So this is the problem 7. Next, the problem is use 7 invariants, that is the moment invariance, to represent a shape, and for this write a MATLAB program for shape representation. Also show the 7 moments are invariant to translation, rotation, scaling and reflection. So corresponding to this original image you can determine 7 moments, that is 7 moment invariants you can determine to represent a particular shape. So corresponding to this original image you can determine 7 moment invariants. After this we have to prove that the 7 moments are invariant to translation, rotation, scaling and reflection. So this image can be rotated. In this case I am rotating the image by 45 degree, rotated by 90 degree. I can do the scaling, I can do the translation, and also I can do the reflection of the original image. So for all these cases I can determine 7 moment invariants, and from this I can prove that 7 moments are invariant to this transformation. The transformations are translation, rotation, scaling and reflection. So the problem is corresponding to these images I can determine 7 moment invariants, and with the help of the 7 moment invariants we have to prove that these moments are invariant to translation, rotation, scaling and reflection. So this is one important problem. So you can write MATLAB program or maybe that Python program for this assignment. This is about the question number 8. Next one is the question number 9. Determine the radon transform for tomographic images and show the sinogram. Show the back projected images. So suppose if I consider the original image, this is the original image, I can determine GS theta, that is nothing but the radon transform of the input image. So that I have to determine GS theta. And the GS theta can be represented as an image, and that is called the sinogram. So how to determine the radon transform? We have to compute GS theta. There are two parameters, one is S, another one is theta. After determining GS theta, we can display the GS theta as an image, and that is called the sinogram. After this, I am considering the reconstruction of the image, and in this case I am considering the back projection technique. So for different angles theta, I am doing the back projections. So I will be getting the back projected images. So from number of back projected images, I can reconstruct the original image. So for this I have to determine the ray sum. So ray sum also I have to determine, and this ray sum or this GS theta can be displayed as an image, and that is called the sinogram. And reconstruction is nothing but for different theta, I have to determine the back projected images, and from the back projected images, if I combine all the back projected images, I can reconstruct the original image. So this is the reconstructed image by considering the back projection technique. There are two techniques in my class I have explained. One is the back projection technique, another one is the Fourier transform technique. But in this case I am considering the back projection technique. You can also apply the Fourier transform technique. So corresponding to this I am showing the program. So first I have to read the original image. So this is the original image I am showing. After this, what I am considering, I am finding the ray sum in different directions, in 90-degree directions, in along the 0 divided by 180 degree, like this, all the directions I am determining the ray sums. So that means I am calculating the ray sums. After calculating the ray sums, what I am considering, so ray sums along the 135 degree, adding the ray sums 45 degree like this. So I am showing the reconstructed image because I am doing the back projection at different angles, and from this back projected image I can reconstruct the original image. So that means I am considering the ray sum in different angles, different directions, and after this I am reconstructing the original image from this back projected images. That is about the sinogram and the reconstructed image. So for the sinogram I have to determine the GS theta. The next program is write a program to implement KL transform of an image and show the transform image, represent the image in terms of eigen images and show the results. So in the KL transformation, so what is the transformation? Y is equal to A x minus mu x. That already I have explained. So A is the transformation matrix. This transformation matrix A, that is determined from the eigenvectors of the covariance matrix. So x is the input vector. So from the input vector I can determine the mean, and also I can determine the covariance. From the covariance matrix I can determine the eigenvalues and the eigenvectors. So EI is the eigenvectors and lambda I is the eigenvalues, and from this I can determine the transformation matrix. So A is the transformation matrix. So if I apply this transformation y is equal to A x minus mu x, then I will be getting the transform image something like this. So this is the transform image. After this I can reconstruct the original image. If I consider all the eigenvectors and all the eigenvalues, then the perfect reconstruction is possible. So what is the reconstruction formula? The reconstruction formula is A transpose y plus mu x. So by using this I can reconstruct the original image. So already I have explained that if I consider all the eigenvalues, eigenvectors, then I will be getting the original image. But if I consider the truncated transformation matrix, then in this case I will not be getting the original image, I will be getting the approximated image. So if I consider all the eigenvalues and the eigenvectors in the transformation matrix, then in this case the perfect reconstruction is possible. But if I consider only some eigenvectors for the transformation matrix, then the perfect reconstruction may not be possible. So this is about the image reconstruction in case of the KL transformation. The next problem is write a MATLAB program to extract shift features of an image. Show the extracted features. So first what we have to consider, first I have to consider the scale space representation. After this I have to consider the difference of Gaussian, and from the difference of Gaussian roughly I can locate the key points, because I have to find the extrema, I have to find the maxima or the minima of the difference of Gaussian, and from this I can determine the roughly the key points. After this I have to neglect the low contrast key points and also the edge pixels corresponding to the key points. So by considering the Hessian matrix I can remove the edge pixels which are detected as key points. After this I have to do the orientation assignments, and finally the shift descriptors I will be getting. So here you can see I am showing the key points corresponding to this input image. These key points are the shift features. So I will be getting the shift features and I will be getting the descriptor, and the size of the descriptor is generally 128. Question number 12. Write a MATLAB program to extract Hawk features of an image. Show the extracted features. So Hawk principle already I have explained in my class, the histogram of oriented gradient. So you can get the feature vectors based on the gradients. So gradient of an image you can determine, and from the orientation of this gradient you can determine the feature vector corresponding to the input image. So you take one input image and corresponding to this you can determine the Hawk features, and with the Hawk features you can detect objects present in an image. That is nothing but object detection. That is question number 12. Question number 13. Write a program to detect edges of an image by Kenny edge detector. So this problem is the detection of the edges by Kenny edge detector. So here I am showing the input image. For Kenny edge detection, first I have to do the Gaussian blurring, that is the image is convolved with the Gaussian, that means the noises are removed, and after this I have to determine the gradient magnitude and also the orientation, that is the direction of the edge normal. Here you can see I am determining the gradient magnitude and also I am determining the orientations, that is the direction of the edge normal. So first step is to convolve the image with Gaussian. The second step is I have to determine the gradient magnitude and the direction. So you can see I am determining the gradient magnitude and I can determine the angle. After this the next important step is the non-maxima suppression. So that concept already I have explained, and the non-maximum suppression, and after non-maximum suppression you have to apply the concept of the thresholding with hysteresis. So for this you can consider the low threshold and the high threshold, and based on this you can determine the edge pixels, and you can see that finally the edges are determined, that is the edge pixels are determined with the help of the Kenny edge detector. So this is the concept of the Kenny edge detector. So the main steps already I have explained. So first I have to do the convolution of the image with the Gaussian, that is the noise reduction using a Gaussian filter. After this I have to determine the gradient magnitude. So first I have to determine the gradient along the x direction and the gradient along the y direction, the horizontal and the vertical directions. After this I can determine the gradient magnitude, and also I can determine the direction of the edge normal. After this the non-maxima suppression, that principle I have to consider, because in this case I have to see the neighborhood. So based on the neighborhood I can apply the principle of non-maxima suppression. The next one is the thresholding with hysteresis. So that means I can consider two thresholds, one is the low threshold, another one is the high threshold, and I can determine the strong and the weak edge pixels. So that is the thresholding with hysteresis, and finally we can do the edge linking. So these are the steps of a Kenny edge detector. So the corresponding program you can see, I am considering the input image. So this input image I am converting from RGB to gray, that is RGB image is converted into gray, and this is the input image. After this I am doing the Gaussian blurring, that is the image is convolved with the Gaussian, and we can determine the x gradient and the y gradient, that is the gradient along the x direction and the gradient along the y direction I can determine. And also I can determine the gradient magnitude and also the angle I can determine. And after this I can plot the gradient magnitude and also the directions, the direction of the edge normals. So this I can plot. So these are the first and the second steps. After this I can consider the non-maximum suppression. So that means I can consider the quantization of the all possible directions into 4 or 5 directions, because I have to search the neighborhood pixels. So for this I am doing the quantization of all the directions into 4 directions. So here you can see I am considering the directions like this, and based on this I am finding the neighborhood pixels. After this I have to apply the principle of the non-maxima suppression. So you can see I am applying the non-maxima suppression and I am getting the intermediate image. So this is the intermediate image. After this I am considering the thresholding with hysteresis. So for this I am considering 2 thresholds. One is the low threshold, another one is the high threshold. And after this I am applying the thresholding with hysteresis principle, that principle I am applying. And corresponding to this I will be getting the edge pixels, and these edge pixels of the input image you can display, you can show. So these are this is the concept of the edge detection with the help of Kenny edge detector. That is the MATLAB program. Similarly, I can consider the same thing, that is the Kenny edge detector, by considering the Python programming. So just I am giving one example of the Python programming here. So first I am considering import NumPy as NP. So what is NumPy? NumPy is an open source numerical Python library. So if you read the Python library, then you will get this one. So it is an open source numerical Python library. And what is available in the NumPy? So NumPy contains a multi-dimensional array and matrix data structures, and it can be utilized to perform a number of mathematical operations on arrays such as trigonometric operations, statistical operations, algebraic routines. So all these operations we can perform with the help of this library, that is the NumPy library. And one is the Pandas. Pandas is an open source Python package, and that is most widely used for data science, data analysis, or in machine learning also we used this Pandas, and it is built on top of the NumPy package. So this Pandas is also another library. And you can see import OS. What is OS? The OS module in Python provide functions for interacting with the operating system. OS comes under Python's standard utility modules. So OS means the OS module in Python provides functions for interacting with the operating systems. So that is OS. After this, next one is import CV2, that is nothing but OpenCV Python. So OpenCV Python is a library of Python designed to solve computer vision problems. So suppose if I consider, suppose CV2 dot suppose imread So if I consider this statement CV2 dot imread, this one, so it loads an image from the specified file, and suppose if the image cannot be read because of missing file or unsupported or invalid format, then this method returns an empty matrix. So import CV2 means it is a OpenCV Python, so it is used for computer vision problems. So after this I am considering import matplotlib, that is a collection of functions that make matplotlib work like MATLAB. So we can create the figure, we can do the plotting like this with the help of matplotlib. So this is a library, the import this one. After this I am considering the Kenny edge detector in Python. So here you can see conversion of the image to grayscale. Again I am converting the image into grayscale. Suppose the RGB image is available, so we can convert the image into grayscale. After this we can do the Gaussian blurring. So you can see I am doing the Gaussian blurring. After this I am considering the Sobel operator to determine the gradient magnitude. So we can determine the gradient magnitude, we can determine the gradient along the x direction and the gradient along the y direction, and from this we can determine the gradient magnitude. After this we are considering the concept of the non-maximum suppression. So all these angles I am considering, like 22.5 degree plus 90 degree plus 135 degree. So quantization of all possible directions into 4 directions by defining the range. So that means I am defining the range and I am doing the non-maximum suppression. That means I am finding the neighborhood pixels, and based on this I am doing the comparisons, and from this I am getting the non-maxima suppressed image. After this what I am considering? I am considering the thresholding with hysteresis. So for this I am considering the strong threshold and the weak threshold also I am considering, and I will be getting the strong edge pixels and the weak edge pixels, and finally I can get the edge pixels and I can show the output image and the input images. So this is the Python programming to show the Kenny edge detector. So like this you can write either MATLAB program or the OpenCV Python program. So corresponding to this you can see the input image and the output images. So edges are detected in the output image, that is the edge detection by Kenny edge detector. Next problem is write a program to detect lines and the circle by half transformation. So corresponding to this image I am determining the lines and the circles by considering the half transformation. So this principle already I have explained in my class. So for this we have to consider the parametric space. The parametric space is rho theta is the parametric space, and mainly I have to do the voting. So for this I have to first initialize the accumulator, and after this I have to go for the voting corresponding to the pixels, all the edge pixels if I consider, and from this I can determine the, or I can detect the lines, I can detect the circles. So you can see this is the parametric space. I can show the outputs in the parametric space, and based on this voting I can detect the lines, I can detect the circles. This is question number 14. Write a program to balance a color image. So here you can see I am considering the input image, that is not color balance. The colors are improper, so I have to balance the colors. So simple procedure is, suppose corresponding to a known region, suppose if I consider this is the known region, corresponding to this, this should be white, this should be white, but in this case I am not getting the white. So corresponding to this known white portion, R should be equal to, G should be equal to, B should be equal to 1, but actually I am not getting the white color. Similarly if I consider this is the black, so this is the black color, but I am not getting the black color because of the imperfection of the image capturing device. So what I can consider, I have to consider the color balancing principle. So corresponding to the known region, suppose white region I am considering, R is equal to G is equal to B is equal to 1. Now suppose make one component fixed, suppose I am making R fixed, and find the transformation for other two components, that is the G and B, so that R is equal to G is equal to B is equal to 1. So I have to make one component fixed and find the transformation for other two components, so that R is equal to G is equal to B is equal to 1, and apply this transformation for all the pixels of the image. So apply this transformation for all the pixels of the image, and after this if I apply this transformation I will be getting the color balance image, that is the output. So I am getting the color balance image in the output, that is called the color balancing. So you can write a MATLAB program or maybe OpenCV Python program for this problem. Next one is write a program for vector median filter and show the results for a color image. So here I am showing one input image, Lena image, and this image is corrupted by noise, that's salt and pepper noise. And after this I can remove the salt and pepper noise by considering the vector median filter. So I cannot apply the scalar median filter in case of the color image. So that concept also I have discussed in the class. So for removing the salt and pepper noise in the color image, I have to apply the vector median filter. So what is the program for this? You can see. So first I am considering the original image, and after this I am applying the salt and pepper noise, and we can display the image, the original image with noise. After this mainly I have to determine the distances. So I have to consider one window, and in this window I have to consider the distances. So distances in terms of RGB value. So that is nothing but the Euclidean distance I have to determine. The distances in terms of RGB value. So you can see the distances in terms of the RGB value, R minus R, B minus B, like this, G minus D. So I am finding the distance in terms of RGB value, and I have to find the minimum distance. So this is the minimum distance I have to find, and based on this I can find the median value. So median value I can determine, and after this I can display the output image, that is the salt and pepper noise can be removed. So this is the program for the vector median filter. And the question number 17 is, write a program for image segmentation by k-means clustering. So input image I am considering, and you can see I am doing the image segmentation by considering the k-means clustering. First I have to consider the means. So randomly I have to select the means. After this I have to update the means based on the minimum distance of the algorithm. The algorithm is the k-means clustering. So you can see the program. So first I am initializing the means, mean 1, mean 2, mean 3. 3 means I am considering. After this I have to find the distance between the sample points and the means, and after this I have to update the clusters. So I will be getting the new cluster centers. This process I have to repeat again and again until the no change of the means, and after this finally I will be getting the segmented output image. So that is about the k-means clustering. The problem number 18 is, write a program for motion estimation by optical flow. So here I am showing two examples. One is the input image. I am considering the frames of the input video. Here I am showing 2 frames only, and similarly for the second case also I am showing the input image frames corresponding to a video, particular video. And after this I can apply the optical flow principle. So I can determine the optical flow. You can see the direction of the optical flow, and similarly you can see the optical flow directions I can determine from the input image frames. So you have to apply the principle of optical flow. So this also you can do in MATLAB or maybe in OpenCV Python. So this is a very interesting problem. Next is question number 19. Write a program to recognize faces by PCA and the LDA. So any database I can use, and in this case I have to first determine the eigenfaces for the PCA, and for the LDA I have to determine the Fisher faces. So here you can see I am showing the eigenfaces. So the principle is, any unknown face can be represented by a linear combination of eigenfaces. So these are the eigenfaces I can determine. These eigenfaces I can determine from the eigenvectors of the covariance matrix. That means from the input vector I can determine the covariance matrix. From the covariance matrix I can determine the eigenvectors, and that can be displayed as an image, that is nothing but the eigenfaces. So any face can be represented by a linear combination of the eigenfaces. So these are the eigenfaces, and similarly I can also determine LDA faces. So I have to apply the LDA principle, and I can determine the Fisher spaces. So that means I have to determine the Fisher spaces from this matrix, that is the within scatter matrix inverse into SB, that is the between scatter matrix. So from this you can determine the Fisher faces. So these are the Fisher faces. The last problem is, read the frames of a video one by one and then convert them to a color video, that is nothing but the pseudo coloring, that is the false coloring. Segment out different objects, vehicles, person, etc. from the input video and then determine the trajectory path showing the motion of the two vehicles. So in this case, in this input, you can see I am considering the frames of a video. So these are the frames of a video, and I have to determine the moving objects. So simply you can apply the sense detection algorithm for determining the moving objects, or maybe you can apply the optical flow algorithm or any other algorithms you can apply. But the simple one is the sense detection algorithm to determine the moving objects. And for the pseudo coloring concept can be used to convert the black and white image into color image, the grayscale image into color image. So I am applying the pseudo coloring principle, and you can see the outputs. So I am converting the grayscale image into color images. So this transformation I can apply for pseudo coloring. So first transformation is for the R component. Suppose this is the transformation for the Z component, and this is the transformation for the blue components. And you can see if I see the transformation, there is a difference in the phase and the frequency, and for this I am getting the false colors, and corresponding to each portion I will be getting different colors. So corresponding to this portion I will be getting one color, corresponding to this portion I will be getting another color. So this is the concept of the pseudo coloring. And you can see corresponding to this input image, I am converting the input image into the color image, and also by applying the sense detection algorithm I can determine the moving objects, and corresponding to this I can determine the trajectory. So even you can apply the optical flow algorithm. In this class I have given some examples of programming. I have given 20 examples, the programming examples. I feel you should do programming to understand the concept of image processing, the concept of computer vision, and also the machine learning algorithms. If you do programming in MATLAB or any programming languages, your concept will be clear. Initially I thought that I can cover many topics, particularly the applications of computer vision, but in 30 hours course it is not possible to cover all the applications of computer vision. So that is why I have to stop here, because already I have covered 40 hours of the lectures. So maybe in the next time I can discuss more applications of computer vision. So I hope you have enjoyed the course. Thank you.